Let's talk about single slit diffraction now. Huygens principle will be our guiding principle with single slit diffraction. We saw that light formed an interference pattern with two slits. It also turns out to be true that light will form an interference pattern when passed through a single slit. Huygens principle says that every point in a wave acts as a source for a spherical wave, which are the flashing yellow bright spots in our animation here. We're coming across a yellow barrier that has a single slit in it, and each point of space there acts as its own spherical source. A wave passing through a single slit will diffract and to create an interference pattern with itself then. This is most noticeable for narrow slits. And by narrow, I mean that the width is at most around 1,000 wavelengths of your light wave long. So, quantitatively determining where dark spots will form on a single slit interference pattern. So that's what's next. We're going to do dark spots, not bright spots, and you'll see why. So here's the picture first. We have a single slit, and we have bright, dark, bright, dark, bright, dark, alternating, and we are going to be able to locate the vertical location of those dark spots, y1, y2, etc. Here is the relevant picture, and my bubble's going away. Okay, so here is an expanded view of the slit, and we've numbered a certain number of those sources, 1, 2, 3, up through 12. And we can see that the light moving toward the Y1 dark band, that all of our light's moving toward the Y1 dark band. Waves 6 and 12, labeled here, 12 and 6, are separated by a distance that's equal to half the width of the slit. So the distance that separates them is the width W of the slit over 2. They're halfway between the separation distance is half the width. Okay. The first point of destructive interference will occur when d sine theta, that's our geometry factor from this experiment, is equal to m plus a half lambda. And the distance between those two waves, 6 and 12, is half of the width. And the first destructive interference point is when m is 0 and we're half a wavelength apart. Similarly, you'll get dark spots for 5 and 12 and so forth at those same points. So multiplying this equation by 2, we are going to get a dark spot every time that W sine theta equals lambda. That'll be our first dark spot, that is. And then the mth dark spot will be whenever W sine theta is equal to m times lambda. When we switch from bright to dark, because we're talking about interference now between successive waves, or not successive waves, but waves that are only half the width apart. So that's why we've switched from bright to dark, is because we've shifted the separation distance to just be half the wave. Let's talk about this equation some more. In particular, I want to compare and contrast the double slit and single slit diffraction equations. For a double slit experiment, d sine theta equals m lambda. D is the separation distance, theta is that angle from the point between the slits to a point on the screen. M is the order of bright spot you're talking about, lambda is the wavelength. Single slit is W sine theta equals m lambda, where W is the width of one slit. So D is the separation distance between slits in a double slit experiment. W is the width of the one slit you have in your single slit experiment. In a double slit experiment, the slit width is assumed to be infinitely small or negligible relative to the separation distance between each slit. The slit cannot be infinitely small for single slit diffraction. You need some width to allow the wave to interact and interfere with itself. This equation for double slits gives you the bright spots. whereas we get dark spots for a single slit diffraction because the waves that are diffracting are only half the width apart. The probably most relevant to you difference is that the double slit equation is on the AP Physics 2 equation sheet, but the single slit equation is not. So you need to know how to go from the double slit equation to the single slit equation and know these differences in our compare and contrast here. All right, so that's single slit diffraction. We'll do some practice in class. Hope that was helpful, folks.